talk about the IP protocol, the internet protocol. Do have to warn you, I've been traveling for 24 hours. I've been up for 24 hours, so might be a little, um, this might not be my best lecture, but bear with me. I'll try to go slow, and we'll see where it goes. Uh, Today we're really just going to talk about the datagram format and addressing. This has actually a lot to it. We'll spend another next lecture on, that'll be a Monday lecture though, on NATing, network address translation, and IPv6. Just to remind you, the network layer lives right, up below the transport layer, above the link layer, but actually quite a bit going on. Because remember, there's the control plane and then there's the data plane. So here we have like a whole set of algorithms designed just for the control plane, OSPF, BGP, things like that. These are protocols you may have heard of, maybe you haven't. Those are all to help you determine what should go in your forwarding table. So that's a whole suite of protocols. On top of that, there's also the data plane, the IP packets. That's actually what contains the data between the different applications that you're using to get actually work done on the network. There's actually a third suite of protocols called ICMP, Internet Control Message Protocol. And this is for like error handling. So if something goes wrong on the network, in theory, the IP layer can send a response back to the original node, say, hey, this thing happened. You don't have to honor that, so it is becoming less and less common. It's still done, but it's becoming a little bit less common to support ICMP, because really you're just being a good citizen. There's no requirement that you have to do that. Okay, so here's the header for IP. Pretty large, right? And there's a lot going on here. I would ask you what stands out to you, but since you're not here to answer that, we'll just kind of go through it systematically. So first we have a version. I think this is the first protocol we've seen with a version. In my opinion, that's always a good idea to have that, because if you ever change what these headers mean, then you're going to want a version to know, okay, well, how do I interpret these headers? So in this case, IPv4 versus IPv6, that changes quite a bit what this header looks like, and so they have a version there. They have the header length in bytes. Question that you might think about is, why do we need a header length? Similar to TCP needed a header length. And the answer is the same. It's because we have this options right here. So this header can be variable length. If we don't have any options, then it'll be shorter, but if we have some options, it'll be longer. So we need some way of knowing where the start of the payload is relative to the rest of the header. There's the length in bytes, similar to UDP. It's 16 bits, so you could, in theory, hold 64K bytes of data, but the maximum unit, transmit unit, MTU, is typically more like 1,500 bytes or less. And there's a lot of that actually is impacted by the link layer, and so it doesn't make sense to make giant IP packets like 64 kilobytes. Then we have the types of service. So this is a new field we haven't really seen before. This just describes, well, like what is this that I'm sending? What's the type of service I'm providing? Is it have some quality assurance to it? Normal IP does not, but diffserv and ECN could potentially have different types of service associated with them. Then we have the time to live. Now, people get this confused, because it's named poorly. I don't think it should be time to live. It should be hops to live. So what this is doing is, what if you had a packet that was going through your network and there was something like a routing loop, which is a thing that can happen where your routers aren't quite synchronized quite yet. They're settling in, and there might be a loop in your network such that one router passes another, and they'll pass another, and then they just go in a circle, passing it to each other. You don't want that. That packet could be in there for a really long time if you kept doing that. So that's what this time to live. It's not the time, though. We don't actually worry about how long it takes. We look at purely the number of hops. So what we do when we send a packet, we put a number in here. It's operating system specific, but you put some number in here, like let's say 64 or 32, and then you say, okay, every time it goes through a router, I'm going to decrement that. I'm going to subtract 1 from it. And if a router gets that a packet and the time to live is 0, then it says, okay, I need to drop this packet. And it just is supposed to drop it. It's not supposed to route it, because that could be indicative of a routing loop. So that's the time to live. This is actually how traceroute works. Is traceroute doesn't put the default value for this, the normal value for the time to live. Actually, it starts out with, let me put a time to live of 1, and then it sends it to the router, and the router is supposed to respond, say, hey, I threw away this packet. And then that's how traceroute works, is it gets response back from routers using ICMP, and says, okay, I got an error from this router. That means, and how long did it take? And that's the next router. And then it increments it by 2 and does the same thing, and then 3, and so on. That's how traceroute works. It takes advantage of this time to live field. Okay, now we have an upper layer field. That's a new one as well. We haven't seen that before. It helps us to determine if it's TCP or UDP or another one. And that matters because of this connection, this really tight connection between IP addresses and port numbers. So we need to know if it's TCP or UDP, where to look for those port numbers. Okay, we have some flags. These are used for fragmenting a packet. We'll get to that later on. And then we have the checksum. Similar to the checksum, we have a TCP and UDP. Got our 32-bit addresses, source and destination. I want to highlight that they're 32-bit. How many addresses can that actually support? 2 to the power of 32. That's quite a bit of addresses, but the internet's pretty large. We've actually run out of IP addresses, publicly accessible IP addresses. And so that was kind of the advent of IPv6 to say, how can we solve this problem? There's a nice quote I like from one of the creators of the internet. So we didn't know at the time what it should be. So 32 bits seemed like a reasonable number. They didn't have any expectation that it would turn into this crazy big thing where they'd run out of space. Okay, and then we have options. We won't really talk about this, but there could be some additional information you might want to include in the header. Okay, so if we add that all up, we have 20 bytes of data. And we can't forget that TCP right here has 20 bytes of data. So that means we need to send a packet of data from like the application layer. We're going to have at least 40 bytes of data we're going to be sending. Now for Wi-Fi, Ethernet, that's not that bad, but for like Bluetooth, that's a huge overhead. So be thinking about that. We'll talk about that at the end of this class. This course of how wireless protocols, especially like lower data rate wireless protocols, deal with this problem. Okay, so that's the header. I don't know, nothing particularly that crazy. So lots of new concepts here though. So this is worth thinking about. If you're going to design a protocol that has some of the features of IP, you'd want to probably have some of these similar kind of fields in here. Okay, so let's talk about IP addresses. We've done a lot with them. You've seen them. We talked about DNS, but let's really finally concretely define what an IP address is. Okay, so we know it's a 32-bit number, some kind of identifier. We often write in this decimal dot notation, what it's called. So each byte is represented by its own number from 0 to 255, and then they're separated with a dot between. So we have 4 of these. And so it identifies a host, like a computer, or a router's interface. So a router can have lots of different interfaces. In this case, it's only 3, but there could be a lot more for a router. And so it identifies each one. Now, interface, and I think I said that kind of wrong. Host interfaces can identify as well. So not just a host, because a host can have multiple interfaces. Like my laptop, I plug it into Ethernet all the time. So it has an Ethernet interface, but it also has a Wi-Fi interface as well. So in that case, it will actually have 2 IP addresses. That's not super common for laptops or even desktops to have multiple interfaces, but it's not uncommon. Whereas routers is much more common to have multiple IP addresses. So interface is what connects the physical link to the network. like I said, we write in the decimal dot notation. But I just want you to remember that like it's just binary at the end of the day, so it doesn't really matter how we write it, right? It's just, this is binary. We could write it in different ways. In fact, MAC addresses, which we'll cover in the layer below IP, writes in a different way. They're a little bit longer, but they also write it in a hex format. So it doesn't really matter. That's just convention, but at the end of the day, it's just the same data. So how are these interfaces actually connected? Here we have the kind of this cloud, and there's lots of ways to connect these devices, but we're not going to talk about that. We're going to abstract away. Let's not worry about it. It could be a router, or sorry, a switch. It could be an access point. Let's just like pretend like they're not there, and that just somehow magically they're connected to this router. We don't need to worry about those details yet. We'll learn more about those later on. Okay. So IP addresses, it's this dot decimal notation. To make IP addresses a little bit more, I want to say efficient, but also more like organizable, we've broken them up into subnets. And you can have subnets within subnets within subnets. You can kind of keep breaking it up. So you're going to say, I have one network, but I'm going to have different subnets associated with that. So in this figure right here, we actually have 3 subnets. And you can tell because they have different IP address ranges, right? So here on this subnet, it's 223.1.1. Then over here, it's 223.1.2. So the first 3 bytes are denoting the subnet. And then here we got 223.1.3. So they all share that in common. The only part that they don't have in common is the last dot. That's different for each host. That uniquely identifies them on the subnet. We'll get more specific on how we determine how we knew what part was the subnet. But kind of from a high-level overview, we can define a subnet to be any grouping of computers and devices with that don't go through a router. So as soon as they go through a router, then they become a different subnet. Once again, we don't really care how they're connected. That could be over Wi-Fi, could be over a router. Sorry, I meant to say a switch. We don't really care, but it's just a grouping of computers that are connected that don't go through a router. That's what a subnet is. So as I kind of already said, there's 2 parts to this IP address. There's the subnet part, the part that uniquely identifies what subnet you're on, and there's the host part, the remaining bits of information that are in the IP address. So IP addresses definitely have structure associated with them. That's partly how we're able to determine their location, is by what subnet they're in, and going all the way down to a specific region or ISP, internet service provider. Okay, so this is a way to kind of think about defining subnets. You could unplug everything, and all the islands are considered a subnet. Okay, so how we mark subnets is we use this /24. And what that's called, okay, sorry, let me get, where is that slide? That's called CIDR notation. I'll go back to those slides in a second. It's called CIDR notation, classless interdomain routing, pronounced CIDR. So it's the IP address /x. And what x tells us is how many bits of this IP address is the subnet portion. So previously we saw 24. That means 24 of these bits, so it's right at this decimal place, was the subnet. So first 3 bytes were the subnet, and then the last byte was the host part. Now it doesn't have to be evenly divisible by 8. That's the power of CIDR notation, is that it can actually be 23 or 6. I don't know. It can be any number you want, x, within the range of 0 to 32. You don't see that. It's common to see 24, but you can do that. You might have seen a kind of different way of writing this with Windows. That's where I've commonly seen that. I guess my Mac does that as well. So if I draw here real quick, you might see like 2, 5. Oh man, this is bad. 2, 5. The subnet mask is another term. I'm sorry. 5 So this is kind of telling us the same part of it. It's like, well, what part of this is a subnet? It's the mask, and then what part of it's IP address? And so you can think of these as all ones, and you can kind of AND it with your IP address, A dot B dot C dot D, and then you'd say, okay, I'm gonna AND these together, and so I'm left with A dot B dot C dot 0. And so now I know that this part is my subnet part, and this part right here is my host part. So that's another way of doing it. Subnet masks, that's common on operating systems, but the more general form, and the one we'll be mostly covering in this class, is the CIDR notation. Okay, let me clear these. Okay, so going back to here, so this, you can have lots of subnets all linked together. Here we have the /24, so we know that these first 3 bytes of every IP address is the subnet part, and the last part right here is the host part. Okay, so hopefully that makes sense. There are some special IP addresses. I wanted to go over that with you guys real quick. Let's see, discard that. So let me pull up the Wikipedia page. Oh, here it is right here. There are some special IP addresses that you should be aware of. You've seen some of these already, or I've maybe alluded to some of these already. The ones you'll want to be familiar with is 192.168.0.1. That's a common, most people's homes use this. This is called a private network. So these are, and then there's a few other popular ones, the 10 dot. So this one up here, that's what BYU uses. And then there's one that's less commonly used. Where are you? 172.16. So these are private IP address ranges. These mean that they're not allowed to go out onto the regular internet. They're only meant for internal network stuff like a BYU campus or your home network. If for some reason an IP address left your network with one of those IP addresses, then a router would drop that instantly. It would not be able to route that because those are not routable. So what that means is that every home, in theory, could be using 192.168. And that's okay because they're staying within the home, those IP addresses. So we're able to reuse IP addresses in homes or in private networks without causing any other problems with any other private network. You've seen 0.0.0 before. That kind of means like this network or all the interfaces. And then the last big one is 127.0.0.1. That means like my computer, local host, or the loopback address. So you'll see that commonly. Sorry, there's one more I forgot to say. 255.255.255.255. That is a broadcast address. So if I want to send it to everyone, I don't have a specific person in mind, I don't know what their IP address is, then I can broadcast it out and say, hey, everyone on this network, hear this message. And so how I denote that is with all ones in the IP address, or 255, dot for all 4 parts. So those are the important IP addresses I want you to be aware of. There's other ones like, internet IP addresses and, regular stuff, but those are the ones, and it tells you how many hosts. Oh, sorry, I forgot to say that. Let me go back to this CIDR notation. I don't know if I actually show this diagram. So here we're saying /23, so this is where we draw the line between the subnet and the host part. So what is the thought? Like, why don't I do /31? Like, what would be, put the line right here. What would be the problem with that? Oh, didn't mean to do that. Apologize. Let's draw a pen. So what would be the problem with that? What that means is I can have lots of subnets. That's great. But I can only have 2 computers on each subnet. So that's not as great. So you don't often see that. Let's go the other extreme. Let's say, okay, we want to make, this the subnet part, and then this all the host part. We have the opposite problem. We can only have 2 subnets now, and then we can have tons of hosts. So really, it's up to you to how you want to design your network. I mean, both extremes are not great. Uh, you know, breaking it right here is a common paradigm /24. But what that means is I can only have 2 to the power of 8 uh, devices on my network, 8 hosts, which was at 256 computers on my network. Actually, less because routers need to take up an IP address, and you're not allowed to use the 0 IP address, and you're not allowed to use the 255 address. Those are kind of special. So it's actually going to be less than that. And maybe you're running a campus network and you're going to have more than 250-ish devices. A home network, that's probably okay, 250. But a campus one, that's not going to be good enough. So you're going to want to, if you're running a big network, scoot that in more so you can have more hosts as part of your subnet. Or maybe you're okay with that and you just have lots of subnets. It's up to you how you want to design it. There's pros and cons to both. But subnets help. They're not super secure, but they help with limiting broadcast. So if I broadcast out something like with all Fs, that will only get broadcast out to my subnet. That won't get broadcast to other subnets. So subnets are where we kind of are able to communicate with each other, two computers, without having to have a router involved, and so it can be a little bit faster. And if a router sees broadcast, it's not going to rebroadcast that unless you have special rules set up. Okay. So talking about IP addresses, and there's private, public, this CIDR notation. Hopefully you have 2 questions kind of in your mind of how do you get an IP address, and how does a network get an IP address? So how does the host itself, and then how does the network? Oh, a little crazy there. So those are 2 questions I want to answer right now, and then I think we'll be done with this lecture. So back in the day, the battle days, I guess I'll say, it was hard-coded what IP address your host had. So you would have a desktop, somewhere. It wouldn't move much. And some system administrator would say, okay, this desktop has, this IP address, 10.0.0.8. So, okay, cool. And they'd have some kind of record they'd keep of that. They would update the configuration in your Linux or Unix system. And that was fine when you didn't have many computers coming and going, right? When you just had like maybe a computer lab and it was just all static. But that quickly fell apart very fast as mobile devices came on the scene. And so that was not going to work, that approach, to have everything hard-coded. So then we developed a thing called DHCP, Dynamic Host Configuration Protocol. I've also heard it called, plug and play. You can plug your network in and just play on the network right away. So it allows you to dynamically get an address from a server. Get from a server, so that's a typo. From a server. Okay, let's talk about how that looks. So we want to get this, so I want to join the network and I want to say, hey, some server, give me an IP address. And what the benefit of that is, this server can keep track of all the IP addresses given out. And if maybe someone wants to join your network, you can give them the same address over again. But if someone leaves, you can reuse that address later on. If we had done it the old way, where everyone was assigned it statically, then if I didn't go on a campus for a week, then that IP address would still be used or reserved for me. But now if I'm not on campus for this week because I'm out of town, an IP address I'd used in the past can be reused by someone else. So it really plays well with this mobile users that come and then leave the network. These IP addresses can be reused. So there's 4 messages. I think it's easiest just to show kind of how they work together. Only 2 of them are actually required, but we'll show all 4. So one thing you need to have, though, is you need to have a DHCP server. Now, I'll tell you right now that all of you, unless you know otherwise, are using DHCP. That's just what the standard configuration of all laptops and operating systems are. I mean, if you've gone and changed your settings and you've changed it, then you aren't using that. But most people are. But you might say like, well, I don't have a DHCP server in my home network. But actually you do. You don't realize it. It's often built in with the router. So this wireless router you have is doing so many things. It's a Wi-Fi access point, it's a router, it's doing DHCP. We'll learn about next lecture. It's also doing NATing as well, network address translation. It's doing a lot of things. Sometimes it's doing DNS as well. This little box has a lot of duties associated with it, but one of the things for sure it's doing is DHCP. Now, on a big campus network or large corporate network, it's likely you're going to have dedicated servers to handle the DHCP. You're going to have one for every subnet. You could build in the router, but it's kind of more convenient when you have a large network to separate it out. Okay, so we have some client arrive, wants to join the network, and wants to get an IP address. So what it does, and this is really important, we got to pay attention to some things. It's going to join the network and it's going to send out a message. We might say, well, how can it send out a message if it doesn't itself have an IP address and it doesn't even know what the IP address of the server is yet? I mean, we have it listed right here at the top, but it doesn't know that. So it's going to send out this message, and the message is essentially going to be broadcast out. Remember broadcast, right? All 255. It's going to say, hey, server, who's out there? Or is there a DHCP server out there? And that can be a source of issues when you connect up computers without a router, without a DHCP server, is it can't get an IP address. So specifically, it's going to send with the destination IP address of all 255. But then, so that makes sense. That's broadcast. It's going to be broadcast out to everyone. But what's its source address going to be? Think about that. It doesn't have an IP address yet. So how can it put its source if it doesn't have it yet? So in this case, what it does, it kind of cheats. It just puts zeros. It just leaves it blank. It says, I don't have a source IP address. That's why the whole point of me talking to this DHCP server is to get an IP address. So I can't put anything in there. So it puts zeros. Now note this right here, though. I want to highlight this. These are our port numbers. So what does that mean? If we have a port number, that means DHCP is not a network layer protocol. It's not a transport layer protocol. It's an application layer protocol. It's kind of weird. It's like, it's dealing with IP addresses and it's getting me my IP address, but it's an application layer protocol. It's using port numbers, and those are well-defined port numbers. So then this discovery comes out, and this is the optional part. Is if you already know what the IP address of the DHCP server is, then you don't have to discover it, and then there doesn't have to be a DHCP offer. But what the offer is essentially doing is like, yeah, hey, I'm here. You can use me. So it sets the IP address. Oh, do that. Oh. Sets the IP address of its own IP address, but it doesn't know who to send this back to, right? So it has to broadcast it out again to everyone. So it's kind of interesting. You could, if you wanted to, sniff on a network for all the DHCP traffic because the request is broadcast out, so is the response is broadcast out. So the question you might be asking, well, how does then the server keep track of what IP address it gave it if it doesn't know who it's talking to yet? And the answer is through this transaction ID. It has some random identifier that can be used between requests to keep track of it. So the DHCP server is going to hold on to this transaction ID and say, okay, this is associated with this computer right here. Like I said, this would be skipped if you had already maybe joined the network and you knew what the DHCP server was. So then you say, okay, yeah, I want IP address. Once again, we don't have one yet, so we can't fill anything, so we're still going to hit zeros. And then we could put the destination as broadcast, and we have the same, well, it's a new transaction ID, but it's incremented by 1, so it's clear. And it says, okay, here's your IP address. And finally, you get an IP address right there. Okay, so that's the steps that go into getting an IP address. Notice how there's a lifetime associated with it. We don't want to give it forever, right? Because then that's essentially going back to the static case. We want it to last for a certain amount of time. So what's the trade-offs here? Why would we want it to be really short? Really short is if we have a lot of devices coming and going really fast and they're not there for the network very long. We want to be able to reuse those as quickly as we possibly can. at the cost of extra overhead, right? If I say, oh, I want it to be like every second, then that means my client every second is going to have to send a request at the very least and get acknowledgement back from that. Say, hey, can I keep this IP address? You call your lease time. Can you lease it for longer? So we did it like every second. That would be, really, we could be reusing IP addresses really fast, but there'd be tons of overhead for the clients constantly asking again and again and again. So typically it's an hour, but you can set it to whatever you want. BYU, OIT has some interesting stories about that of setting it either too high or too low. The Tanner building during the winter is really popular for people to walk through, and they had this issue where they're running out of IP addresses on that subnet of that building because there's so many people coming through grabbing an IP address using DHCP, and then they'd leave because they'd go walk outside. And so all the legitimate users in that building didn't have IP addresses. They ran out. And so they had to reduce the lease time of those DHCP, requests and response, or I guess the lease of the DHCP IP address much shorter so that it could be reused faster. Okay. I thought I had one more thing to say about this, but I can't remember now. Transaction ID. Okay. It's not just for IP address. I mean, that's what DHCP was designed for, but it's like, well, if you're going to be sending data back and forth between this server and client, might as well send some extra information. Things like, oh, what's the IP address of the DNS server? Remember I showed you in a previous class the DNS servers of BYU were loaded onto my computer. I didn't enter them in there. That was done through DHCP. When I got my IP address, it also said, oh, by the way, here's the DNS server. It's the local DNS server. NetMask, first hop router. So it can have some extra information in there to help a client. I mean, it could get all that information through other means, but just might as well give it to them now while you have them and not wait for them to have to ask for it later on. Okay, so let's go through this example. So here we have a laptop joining the network. So remember, DHCP is an application layer protocol, and it's using UDP under the hood. I don't know if I said that earlier. I don't think I did. So it does all its encapsulation. It sends out a request. That request gets sent. It broadcasts out to everyone. So the IP address is 255.255.255.255. The Ethernet's going to have a MAC address. That's actually similar. It's all Fs. We do hex notation though for for MAC addresses, so it's all Fs there. So it's received by some DHCP server. Okay, processes it up, pops it up there, and says, okay, great. Yep, I'm a DHCP server. Yep, I have an IP address for them. Here you go. And then it puts it all back together and pops it up to the laptop, and then it's able to get all this information. Okay, so the last thing I want to cover in this lecture is how does a network get an IP address? So all that DHCP stuff is actually for private IP addresses, and I want you to be really clear that there's actually, your computer always has two IP addresses. It has a public IP address that the world sees, and then it has a private IP address. And that'll become a little bit more clear when we cover network address translations, NATs. But for now, just assume that the computer has two IP addresses, only one IP address, I guess, but it presents itself as two IP addresses depending on who it's talking to. So this public IP address, how did Google, when I go to google.com, it resolves to IP address. How did they get their IP address? How did BYU get their IP addresses? So the answer to that is that there's these ISPs that give blocks of IP addresses to people, and they keep on getting more and more specific depending on who they're giving it to. And so when we say we're out of IP addresses, that means that all the IP addresses, these blocks, have all been assigned to different companies to use. So we have these different organizations, and they all have maybe the first first 3 bytes of the IP address have been set. That's theirs. They own that, and the rest they Oh no, I guess it's, I missed this right here. There's this line right here. So it's /23. So these all could be different organizations, and then within the organization, they can hand out these IP addresses to whoever they want to, wherever they see fit. So how it might work is you have, like, let's say these two ISPs. And so what this ISP is advertising to the internet is that, hey, if anything starts with 200.23.16, then send it my way. So it's advertising now, and when some data gets received, it then looks at its routing table, says, okay, that goes in this direction, and then the organization then resolves it after that, because it's longer prefix. This is a /23, this is a /20. So this ISP is able to give out a certain amount, depending on how big they give out to each organization. They have a limit on how many blocks they can give out to the organizations. So this is how we're able to then encode some specific information, because there's going to be some ISP that's local to Utah, or at least some IP address range that's going to be local to Utah, and then we can say, okay, that's BYU's IP address range. Okay, so I know where BYU is. It's Provo, so that's, therefore, if I see something coming from that IP address, that means that's in Provo. So that's how we're able to get some geolocation information from an IP address. But other than that, it's not that much more specific. Unlike what the movies and TV show where it's like, oh, I can see them, they're on the roof. It's like, no, it's not that specific. And then we have another ISP that might be advertising a different subnet. So what happens is, what if organization 1 wants to eventually move ISPs over to here? How do we deal with that? And what's really cool about how we've designed the internet, specifically how we've designed longest prefix matching. Remember what that means? I would ask someone to define what that means. So you think about it real fast. What does that mean? It means we look at the longest matching address, and that's where we send the data. So what we can do to take advantage of that is this ISPs are us can now advertise a longer prefix than what this is advertising, because they're advertising essentially the same thing. The first 2 bytes are the same. This one's a little different, but not much different. But any router right here, if it had some data, would look at these and say, oh, this one's longer, so I'm going to route it to here if it matched correctly. If it didn't match, then it might route it over here. But if it matched both of these equally, then it would choose the longest one. That was more specific. And so that allows us to switch out organizations with ISPs and still keep their IP address blocks, because we're able to advertise the longest prefix match. So this ISP can still keep its 199 subnet, but it can also then add additional ones and just make sure it advertises longer. Therefore, this router right here would always pick the bottom one if it matched. Like that. And then the last big question is, well, how do ISPs get the IP addresses? And that's handled by ICANN. They, like I said, they've given out all their IP addresses. It's a company, not a company, sorry, like a organization, I should say, that's in charge of that. And so that's who takes care of that. Okay. Yeah, and I mean, we allocated it, pretty long ago, 2011. That was a while ago. So are we like done with IPv4? Is it lost? Was it a bad idea? We'll talk about that later on when we get to IPv6, the next lecture. I guess it'll be Monday's lecture because we're doing a lab next lecture. IPv6 solves that problem by saying 128-bit address space. Well, I'm going crazy. That's crazy, but it actually hasn't worked out very well. IPv6, not to get too far ahead, because NATs have kind of saved the day, network address translations. So we'll get into that on Monday. I guess we'll be back by then to talk about it. So yeah, NATs and IPv6. Oh yeah, here's the quote from Vint Cerf. Who the heck knew how much address space we needed? When you're designing the internet, you're like, I don't know, man. 32 bits seems like plenty, at the time. Okay, that's it for today. Thanks for hanging out with me. Hopefully, the lecture was okay to follow. I'm going to go to bed now and sleep for a little bit. But I want to make sure I got this before Wednesday. I don't know. Time is weird, right? Because I'm a day ahead of you guys, I think, right now. So uh, hang in there. Keep on working on your labs, and I will record another lecture for Friday's lecture.